If you want to have a better understanding of limits in any scenario in mathematics, it helps to understand limits of sequences. So let's start off with what a sequence is. A sequence is a function from the natural numbers to some set. Side note, I often think of 0 as a natural number, but not here. So just so that we're all on the same page, the naturals for our purposes start with 1. There are generalizations of sequences that use different domains than the natural numbers, but we're just going to focus on those sequences where the input is a natural number and the output ends up in the real numbers. Sequences divert a little bit from the usual function notation. Usually the input in a sequence is denoted by a subscript and not by parentheses. So if you're not a fan of functions, an infinite list is another good way of thinking about these mathematical objects. Since each term of the sequence or output of the function is indexed by a natural number, when we list them, we order them according to their index. Okay, so for an example, let's take the sequence a sub n equals 1 over n. That is also known as a harmonic sequence, and there is quite a bit of interesting mathematics that revolves around these types of sequences as well that we'll leave for another video. It's quick to see that this sequence is decreasing. That is, for every natural number n, the n plus 1th term is less than or equal to the nth term. So we can write our list in a more descriptive way. That is, we have 1 is greater than 1/2, which is greater than 1/3, and so forth. Now, you may have a bit of intuition behind the limit of the sequence, but what exactly does it mean to take a limit? Well, by definition, for a sequence a sub n, the real number L is called the limit of the sequence if for every real epsilon greater than 0, there is some natural number big N, such that all the terms with index n, at least as big N, satisfy the condition that the absolute value of a sub n minus L is less than epsilon. So, that was a mouthful, and if you haven't seen it before, it can be pretty confusing. So what is it actually saying? Well, another way of looking at it focuses on the absolute value of the differences between something in the sequence and L, the limit value. Namely that if someone were to demand the absolute value of the difference to be smaller than some positive real number, then we can give a cutoff in the list where everything after that term satisfies the demand. And we were able to satisfy that demand no matter what the initial demand was. Again, that's not super clear, so let's go ahead and do an example. Let's take the harmonic sequence we had before. The sequence is decreasing and will never be negative, so 0 seems like a good choice for the limit. Now, to actually prove that this is the case, we need to show that for every epsilon greater than 0, we can find some cutoff in our sequence such that everything after that cutoff satisfies the inequality given by the definition. No matter what is demanded, we're going to go ahead and take big N equal to 1 plus the floor of 1 over epsilon, or 1 plus the largest integer less than or equal to 1 over epsilon. It's not clear at all where big N came from, and I haven't produced any intuition for why you would choose this big N. Where a lot of these big N's come from is that you try to figure out what thing will work before you start the proof. So let's just continue the argument. So for any little n greater than big N, we have the absolute value of a sub little n minus 0 is equal to the absolute value of 1 over n, which is just 1 over n. Now that's less than or equal to 1 over big N, since little n is greater than big N. Then we have that 1 over big N is equal to 1 over 1 plus the floor of 1 over epsilon. And that's just using what we chose big N to be. Now the last step here requires a bit more mental work that if you thought about where big N comes from, you might have come across this. It uses a fact about the floor function that is the floor of a number is less than or equal to that number, which is less than to the floor of that number plus 1. And so using this, we have 1 over the floor of 1 over epsilon plus 1 is less than 1 over epsilon, which is just epsilon. So if that was a little bit fast, I recommend taking a minute to look over the argument again, because essentially we're done. For the desired criteria, we found that the absolute value of a sub n minus 0 was less than epsilon. And so 0 is the limit value as desired. But hopefully that should give you a little bit more fleshed out idea of what the definition of a limit of a sequence means and how limit arguments work for sequences. Before we finish up, it's important to note that nothing in the sequence need actually equal the limit value. We just showed that for this sequence, that the limit value was 0. However, there is no natural number such that 1 over n equals 0. Also, limits don't always exist. Think of the sequence 1, -1, 1, -1, and so forth. The sequence will oscillate between 1 and -1, but it doesn't get close to anything in the sense of the limit definition. If you want to be completely rigorous about it, find an epsilon for which there is no big N as described by the definition. Anyhow, that's all I have for you today. I hope you enjoyed this video. If you did, give it a thumbs up and subscribe for more mathematics videos. As always, I am Nathan, this is Chalk, and I will see you next time.